Alrighty, so I'm still the only one here, and that's perfectly fine. I did not get any questions ahead of time. I know it was kind of short notice. So I have a sample test that I'm just going to go through some of the questions on. Apparently, there's some sort of basketball game tonight, so some of you might be preoccupied with that. But I'm recording, and I'll post the recording on our Moodle page, so you could just watch this whenever is convenient for you. I'm just going to go through some of the questions that I've gotten in the Math Tank or through email. And most likely, if a few people have questions on something, then there's other people that have questions as well. So if I don't know if any of you have noticed this, but even though this chapter seems like it jumps around a little bit into lots of different topics, there's a reason that all of this stuff is bundled into one chapter. It's because the same formulas end up being used over and over again in all these different topics. The stuff with the vectors, they have a specific set of formulas they use, and then the stuff with the complex numbers, they it's a different idea, but it ends up using the exact same formulas. And then the polar coordinates, exact same formulas again. So it's lots of different topics, but it's all using the exact same formulas to do several different things. So as we go along here, I'm going to kind of point that set of formulas out, that you should make sure that you know when you do these problems, and hopefully kind of explain some of these ideas so that you're not just kind of randomly throwing numbers into formulas, and it makes a little bit more sense on why you're doing what you're doing. Hopefully the test will go a little bit smoother. If there's anything I didn't cover tonight, or if I skipped through a problem on the screen and didn't end up talking about it, but it's one that you have a question on or you want me to do, just call me, email me, come into the Math Tank. I'd be happy to go over it with you. Just let me know. I'd be happy to help. So I've got the sample test here. And one of the things here in chapter 8 deals with rewriting complex numbers in trigonometric notation. And this notation is kind of weird, but the numbers used in the notation, there's a reason for them. So we can graph complex numbers. You should have learned about complex numbers back in Math 171 or whenever you took pre-calculus. So if we think of the x-axis as the real axis and the y-axis as the imaginary axis, we can graph a complex number. For example, let's say, I'm just going to do something easy, 2 plus 2i. By finding 2 on the real axis and then 2 on the imaginary axis and seeing where they connect. It's technically the point 2, 2, because 2 on the real, 2 on the imaginary, and those are the two numbers that I see in my complex number there. The trigonometric notation, instead of doing this as two separate coordinates, what the trigonometric notation wants us to do is connect the origin to that point and draw a line and say, how far out on that line are you going to go, and what angle does that line make with the x-axis? So to go from 0, 0 to 2, 2, well, this makes a right triangle here. And that right triangle has legs that have lengths of 2 and 2. The horizontal side is the x-coordinate. The vertical side is the y-coordinate. What we're trying to find is the hypotenuse. That is the r value in our trigonometric notation. All we have to do is Pythagorean theorem to get that value. And to get theta, we would just do tan inverse of the y over the x. You need to be careful when you do this, though, in your calculator, because you have to take the quadrant that you're working in into account. So be really careful of your quadrant. Now, sometimes the trigonometric notation wants you to use a radian, and sometimes it wants you to use a degree. So also be careful of the directions on the problem and how they want you to enter your answer. So instead of writing it in the format 2 plus 2i, which might be called standard notation, trigonometric notation is going to get there directly from 0, 0 along a straight line at a certain angle. And we want to know how far along that line, r, and at what angle, theta. How do you get to 2, 2 without having to turn a corner if you just want to go directly there? And that's what the r and the theta tell us. So the 2's are the x and the y. So if we plug these in, r is the square root of 2 squared plus 2 squared, which is 4 plus 4, which is radical 8. And you're probably going to have to simplify that to 2 root 2. And then theta is tan inverse of your y over your x, which is tan inverse of 1, which is 45 degrees. So we need to move 2 radical 2 units out on the 45 degree line. So the trigonometric notation is 2 root 2 cosine 45 plus 2 root 2 I sine 45. Now, where you put the I doesn't really matter as long as it's part of the second term. And I've also sometimes seen the 2 root 2 not distributed. So you might say 2 root 2 cosine 45 plus I sine 45. Both terms will always have 2 root 2 in them. So the trig notation, instead of using the legs of the triangle, the trig notation uses the hypotenuse and the angle to get to the exact same spot. And these are the formulas that it uses. And hopefully those formulas look familiar. We've used them for other things before. So this is how to take a complex number that's in standard notation and turn it into trigonometric notation. You've got to find the r value and the theta value and then write it in this format. It's always r cosine theta plus ri sine theta. Once you know your r and your theta, you just write it out in that format. And again, sometimes they just write the r where it's not distributed. It's in the front with parentheses. So that's one of the first questions on here actually wants you to go in the opposite direction. They give you trig notation and they want standard notation. These problems are actually easier. If we know trig notation and we want standard notation, all we have to do is ask the calculator what this value is. Just ask the calculator what 2 root 2 cosine 45 is. Make sure your calculator is in degree form. So to go from trig to standard, all we have to do is evaluate. So 2 root 2 cosine 45. Ask the calculator. It's going to tell you it's 2. 2 root 2 sine 45. Calculator's going to say it's 2. So the x value is 2, the y value is 2. So x plus iy, or x plus yi, is going to be 2 plus 2i. So trig to standard is really easy. We just need to evaluate the trig expression we're writing out. It's the standard to trig that's a little trickier. We've got to use those formulas. Find the rectangular coordinates of the point 5 to 10. So this problem is giving you a point in polar coordinates, and it wants to know what the equivalent rectangular coordinates are. So this is a completely different problem that deals with what seems to be a completely different concept, when really it's exactly the same. It's going to use the exact same formulas. So what this is telling us is we've gone 5 units out on the 210 degree line, and we want to know what rectangular coordinates are. What are the x and the y? We want to change it to rectangular. Rectangular is an x and a y. So what they gave us is polar, which is the r and the theta. And the r and theta here is the exact same r and theta that we're talking about up here with the complex numbers. So the way that we changed the r and the theta to an x is we had r times cosine theta gave us our x, r times sine theta gave us our y. So x equals r cosine theta, y equals r sine theta. These are the conversion formulas to go from polar to rectangular. So we've got 5 cosine 210, 5 sine 210. Now you may need to use your unit circle and get exact values here. One of them is going to have an exact value and the other one is not, because 210 has...
I do?
Hi. Ooh, yay, we've got a couple people. We've got May and Riley here. I'm just going through some problems in a practice test. If you have any specific questions and you have a microphone, you're more than welcome to interrupt me and ask at any time. I do have the option here for a chat screen. So you're welcome to type things into the chat screen as well if you want, or you can just watch. Up to you. So 210 is in quadrant 3, and that's where sine and cosine both come out negative, which makes sense because we should have, in quadrant 3, we should have negative x and y coordinates as well. So cosine of 210 in my calculator, just make sure I'm in degree mode, is negative radical 3 over 2. So I've got 5 times negative radical 3 over 2. And most likely MyLabs Plus is going to want this as in an exact answer. And sine of 210 is negative 1/2. So when I multiply and simplify here, my point in rectangular coordinates ends up as negative 5 radical 3 over 2, negative 5/2. So if we look at the picture, here's the 210 line. And apparently we went out 5 units on that line. And going out 5 units on that line is the same as going horizontally -5 radical 3 over 2, and vertically -5 halves. That's what we were just able to figure out. The next problem asks for trig notation. I talked about trig notation just a minute ago. One thing I do want to point out on this one, when you decide your x's and your y's, it's normal for there to be a plus there. So make sure that when you assign your x's and your y's, you're saying your y is -8. And when we plot that point, if x is +8 and y is -8, you also need to think about what quadrant that point would be. So if x is +8 and y is -8, that would be quadrant 4. Positive x, negative y is quadrant 4. So when you solve for your angle, you should be typing in a quadrant 4 angle for your answer there. I'm going to actually do that problem. 8 minus 8i in trig notation. So this is standard notation, which means we have an x and a y. So we've gone 8, -8. We've gone down to here. Trig notation is how do we get there? By going directly there from the origin along an angle line. So we want to know theta and we want to know r. And we can make a right triangle. We're going right 8 and down 8. So the r is just the hypotenuse, and theta we can get by doing a tan inverse. But in our calculator, it's going to give us the angle inside the triangle, and we're going to have to adjust it. That's why I wanted to do this one. So the r is just Pythagorean theorem. And we're going to get 64 plus 64, which is 128, which is 8√2. Now for theta, that one's kind of tricky. You do tan inverse of the y over the x, which is tan inverse of -1. Now your calculator is going to tell you that's -45, but MyLabs Plus is probably not going to take -45 degrees because -45 is what we would do clockwise. So to get the angle counterclockwise, that would be a coterminal angle. We add 360 to it, which is 315. So the r value is 8√2 and the theta value is 315. And that is a quadrant 4 angle, so that makes sense. And I'm going to type this in just to make sure, and it will tell me if it's right or not. 8√2 and 315. Perfect. The r value is always just Pythagorean theorem. The theta is always tan inverse, and you just have to adjust the quadrant. Solving the triangles, you're always going to use law of sines or law of cosines. And the way to decide whether you need to use law of sines or law of cosines is whether you have a side angle pair. So in this problem, they didn't label all of the sides, but you can label them. I would suggest that you draw this triangle out on your paper, the sides are always going to be lowercase letters that match the angle across from them. So if this is angle B over here, then that 16 is going to be side B. And then if this is angle C up here, that 21 is going to be side C. So what they've given us is angle B, they've given us side B, angle A, and side C. So what they've given us are values for 3 different letters, which means we don't have any side angle pairs. We have a little b, a little c, and a big A. Since we don't have any side angle pairs, we would have to start this problem off with law of cosines. Oops. So if you had the angle A and side A, or angle B and side B, or angle C and side C, then you could just do law of sines. Law of sines is a lot easier in my opinion. But the good thing about law of cosines is you only ever have to use it once. Because once I use law of cosines to solve for another piece of that triangle, then I will have a side angle pair. So law of sines says that you can set up a fraction between a side length and the sine value of its corresponding angle, and it's going to be the same no matter which pair you do. Now, it works for all 3 of them, but we don't ever set it up with all 3. We only set it up with 2 of them. So we could do the A's equal the B's, or the A's equal the C's, or the B's equal the C's. And our goal is to set it up between 2 of them so that 3 values are known and 1 value is unknown, so that we can solve for that value. So that's why we have to have a matching pair, because we have to know 3 of the values, which means one of the fractions is going to be complete. The law of cosines, you may or may not have noticed, starts off looking like the Pythagorean theorem. So law of cosines, at least one of the variations of it does, is c squared equals a squared plus b squared. But there's another term at the back of it, and that's because law of cosines works for non-right triangles. If it's a right triangle, then you would use Pythagorean theorem. If it's not a right triangle, then you have to add this extra piece at the back so it works for non-right triangles. And it's the minus 2ab, oh, it's law of cosines, sorry, cosine C. That minus 2ab cosine C is our magic little piece that makes it work for non-right triangles. Whatever 2 letters are here are going to be here. And then whatever angle is here will match the side on the other side. And you can set this equation up 3 different ways. So I can also say b squared equals a squared plus c squared minus 2ac cosine b. So a and c are on the right, and then cosine of b is on the right, and side b is on the left. And then we could also say a squared equals b squared plus c squared minus 2bc cosine a. So by adding that 3rd piece at the back, it allows us to use the equation for non-right triangles, and it also allows us to shuffle up all the sides because we're no longer guaranteed that C is the longest side anymore since it's not a right triangle. In your homework, there were a few problems where the triangles had more than one solution. Those were kind of tricky. You know there's going to be two solutions. Depending on what information they give you. If they're ass triangles. Ass is a bad word. They're also bad triangles. So what I mean by that is they give you a triangle where they give you an angle, a side, and a side in that order. So in this triangle, if I gave you angle A is 20 degrees, side C is 72, and then side A is 48. I gave you angle, side, side. That's an ass triangle. Angle, side, side. That triangle could have two solutions. So you need to check it and be sure. The way that you check it is when you do law of sines, you're going to have to do sine inverse. And the trick is with sine inverse, you could have two answers. So I'm going to show you the beginning of this problem. Because we have a side angle pair, we can do law of sines. So I've got both of my A's. I've got big A and little a. So I'm going to set up law of sines with my A's and my C's. So 48 over the sine of 20 equals 72 over the sine of C. And I'm going to solve this for C. So I'm going to cross multiply and say 48 sine of C equals 72 sine of 20. And my goal here is to isolate angle C. So I'm going to divide the 48 over. Now this, I could type that in my calculator. 72 sine of 20 over 48. And get a decimal for my sine C. And just make sure your calculator's in degree mode. And I've got 0.5130 approximately. And now to solve for angle C, I would have to do sine inverse of that. But keep the full decimal on your calculator screen when you do it. Don't estimate it. So I'm going to say sine inverse of the previous answer. And I get C is about 30.9 degrees. Now the problem is, and the way that we could possibly get two answers, is sine is positive in quadrant 1 and quadrant 2. So they might have just given me a reference angle. So I need to subtract that from 180 and see if that's also a possibility. See if that somehow can also make this triangle work. So it might be possible if I subtract 30.9 from 180, let's see, 149.1. C might be 149.1. Now, the way that I'm going to know this is if there's anything left to make angle B. So what I know so far is that angle A is 20, no matter what, because they said definitely angle A is 20. And I think I might have come up with two possibilities for C, 30.9 and 149.1. Now let's see if there's anything left for B. If there's nothing left for B in one of these, then we'll just throw out the idea of a second solution. So there definitely is more for B here, because right now it only adds up to 50.9, and triangles always add up to 180. So in this option, we still have 129.1 left for B. In this option, let's see, 180 minus 20 minus 149.1, there's still 10.9 for B. Yeah, so both of these are possible. These are both still possibilities. So the trick is, you get the S triangle, and I'm not, I am swearing to be funny, but it's the way that you're going to remember it. You get an angle, a side, a side. You want to go clockwise or counterclockwise. You don't want to jump around the triangle. If you see angle, side, side, it's a bad word, it's a bad triangle. Those are the ones that you might have two answers. So when we have to do sine inverse of a positive number, it's possible the calculator gave us a reference angle. So one option is the calculator gave us the correct answer. The other option is it's just a reference angle for a quadrant 2 angle. And so we subtracted from 180 and got the second option. And then we would continue working it from there. We knew two other sides. C is 72 and A is 48. So from here, we're just working it like two problems. Now for both options, we need to figure out what little b would be. And they would come out different for both of them. So that's the trick with the two answer triangles. This one is not an angle side problem, but this one doesn't have any corresponding or any side angle pairs, so we would have to start with law of cosines to get another side, and then we could move on. This one just wants us to find a specific length, and it doesn't have any side angle pairs, so it's just finding a length of one of the sides using law of cosines again. This one is a vector problem, and I definitely want to do a vector problem. This one's fairly easy. All it wants us to do is break it down into components, which is the first step to solving vectors. It says an airplane takes off at a speed s of 223 miles per hour at an angle of 15 degrees with the horizontal. Resolve the vector s into components. So 223 at an angle of 15. So angle of 15 is about right there. When we break vectors down into components, what they're asking us to do is split it up into how much of that speed is going towards changing our vertical direction and how much is going towards changing our horizontal direction or position. So they're wanting us to break a triangle up again. What we know is the hypotenuse and the angle. They're wanting us to split it apart into the legs. So technically, if you think back to polar coordinates, if you think back to complex numbers, what we know right now are the r and the theta. They want us to find the x and the y. And it's the same exact formulas we used with complex numbers and polar coordinates. To break vectors into components, we use the formulas x equals r cosine theta, y equals r sine theta. We have the r, we have the theta, we just have to plug them in and solve. So this is going to be 223 cosine of 15. This is going to be 223 sine of 15. And that's all this problem is asking us to do. I think we do need to type it in the calculator. It says round to the nearest whole number. So it does want us to type it into the calculator and round it to the nearest whole number. But that's all it's asking us to do. They gave us a value that's on an angle, which technically is the hypotenuse of a right triangle, and they're asking us to find the legs. I definitely want to do one where we have to add vectors, because those can be kind of tricky. Sketch the pair of vectors and determine whether they are equivalent. Equivalent vectors have the exact same magnitude in the exact same direction. B is at the point 3, 3. So really it's just finding points here. And G is at the point negative 4, 3. E is at the point negative 4, 1. Let's see. They have created the vector EG. The way that they name the vector tells you what point you're starting at and what point you're ending at. So they're starting at E and ending at G. So they've got one vector that's starting at negative 4, 1. So negative 4, 1. So this has a vector starting at negative 4, 1, and this has a vector starting at negative 4, 1. So automatically I can cross off A and B. And ending at negative 4, 3. So they both have them. And then they have the vector BJ. So starting at B, ending at J. So start at 3, 3, end at 3, 1. So start at 3, 3, end at 3, 1. So here is start at 3, 3, end at 3, 1. So over here, this one starts at 3, 4 and ends at 3, 1. So it's not that one, it's this one, 3, 3 to 3, 1. For some reason, they made that one unit longer by accident and had it start at 3, 4. And if you can't see it, you can make it bigger. So they have it starting all the way up here at 4. So that one's not right. And then they want to know if they're equivalent. And these are not equivalent because you can see the arrows are pointing in different directions. EG is pointing up and BJ is pointing down. So no vectors EG. Both vectors have the same magnitude. We can see they're both 2 units long, but they travel in different directions. One's pointing up, the other's pointing down. So they are both 2 units long, but they both have to have the same magnitude as well in order to be equivalent. This one could be solved with either vectors or triangles. It says 2 airplanes leave an airport at the same time. The first one flies 120 kilometers an hour in a direction of 320 degrees. The second flies 180 kilometers an hour in a direction of 280 degrees. After 5 hours, how far apart are the airplanes? Right away, I would go ahead and multiply my speeds by 5. If it's 120 kilometers an hour, and I'm only interested in knowing what happens after 5 hours, that means that this plane has traveled 600 kilometers, and this plane has traveled 900 kilometers. Okay, so 600 and 900. So if they use anything but 1 hour, I would go ahead and multiply them right away. And then I would graph them, and I want to know the angle between them. This thing's going to form a triangle, and it's just going to be a triangle solving problem. So I'm just going to show you the picture for the setup, and then from there it's just triangles. So we've got 320 and 280. $320 is about there. 280 is about there. the 320 we said was 600, and the 280 was 900. And we want to know how far apart they are after 5 hours. So that would be this distance. We can figure out this angle. That's just the difference between 320 and 280, which is 40. So we know two sides and an angle of the triangle. We're trying to figure out the third side. So the hardest part is trying to interpret that information and draw a picture for it. After that, it's a pretty simple triangle problem. This problem is actually really, really easy. I'm not even going to write it down. These trigonometric forms seem really silly and useless until you actually have to do calculations. If you have complex numbers in trigonometric form and you want to do operations, all you have to do is divide those R values. 16 divided by 2 is 8. And then subtract the angle values. So 20 minus 5 is 15. You can't do that from standard form. If you wanted to divide two complex numbers from standard form, if you remember back to Math 171, how we divided two numbers from complex numbers from standard form, we had to multiply top and bottom by the conjugate and FOIL it all out, and it was a big old mess. So this is one of the major benefits of trigonometric form, is all you have to do is divide the r's and subtract the thetas. A hot air balloon is rising vertically 19 feet per second and horizontally 5 feet per second. And we want to know the speed, which is v. All that is the hypotenuse of the balloon, and the angle theta. So this is just tan inverse and Pythagorean theorem. Tan inverse and Pythagorean theorem. All it is. Remember, tan inverse is opposite over adjacent. And it says round both of your answers to the nearest whole number. Just a simple triangle problem. We probably could have done that problem back in chapter 6. Find the polar coordinates of the point, then express the angle in degrees and again in radians using the smallest possible positive angle. So 4 and negative 4 radical 3. So we did a little bit with polar coordinates earlier. 4, negative 4 radical 3. Let me see. So what we had was going from polar to rectangular. Now we have rectangular and we want to go to polar. So I want to go through this one. So this is an X and a Y, and they want us to get an R and a theta. So that's a positive X and a negative Y. So positive X means to the right, negative Y means down. So we're going into the fourth quadrant. 4 radical 3, that's between 6 and 7, I think. Let me see. It doesn't really matter. Yeah, it's almost 7. But I'm just going to say it's down here somewhere. So when we get there with an X and a Y, we get there by going first horizontally and then vertically. I went 4 units to the right, and then -4 radical 3 down. With polar, we want to go straight there on an angle line. And we typically, even though the angle is inside of the triangle, that's the angle the calculator is going to tell us. That's called the reference angle. The theta in the polar coordinates wants this angle, which is the standard position angle. So it's going to be a quadrant 4 angle. The R value is the hypotenuse. So we keep, everything we do here in chapter 8 keeps going back between the x and the y and the r and the theta. The x and the y are the legs of the right triangle. The r and the theta are the hypotenuse and that angle at the origin. So the r is a little bit tricky because you're going to have a radical inside of your Pythagorean theorem. So r is the square root of your x squared plus your y squared. Now to square this, you're just going to square each piece and just do it slowly and think about what you're doing. And then we're going to add the stuff together. So 4 squared is 16. A negative squared is going to be a positive. And then, so that's always going to come out positive no matter what's in there. And then 4 squared is 16. And radical 3 squared is regular 3. 16 times 3 is 48. And then we've got to do 16 plus 48, which is 64. And that comes out to be a nice perfect square. Square root of 64 is just 8. So the R value is 8. And then we're going to do tan inverse to get our theta. We do tan inverse of the y over the x. And I would just type it in the calculator like that. I wouldn't even waste time trying to simplify it. Now, again, we've got to be careful with the quadrant because the calculator says it's -60. That's because the calculator wants to get there as quick as possible. The calculator thinks of tan inverse as a function. If you look at the graph, yeah, you could get there by going clockwise 60, but we want a standard position angle. We want to go counterclockwise. So you should add 360 to that. And you should really be using 300. Now in this problem, they want you to do it in radians and degrees. So look on your unit circle at what 300 is equivalent to. And I believe it is 5 pi over 3. So in this problem, they want you to answer a bunch of questions. It says, what are the polar coordinates? So that's writing it as a point. So we know the R value is 8. Always look at the blue instructions down here. It says simplify your answer, type an ordered pair, type the coordinate for theta in radians. So here, they want theta in radians. So they want the 5 pi over 3 up here. Whoops. I'm trying to do this from a tablet. It's crazy. There we go. And now it wants it in degrees, and we said 300. And now it wants it in radians. We've already done it. It just wants us to separate it out. We know it's 5 pi over 3. Oh. And I'm gonna post the link to this video, but I'm also gonna post all these little notes that I'm writing down as well. So let me see. Dot product is just a formula, just an easy little formula. If you've got two vectors, the dot product between those vectors, you multiply corresponding components. So you multiply the first components together, you multiply the second components together, and then you add the results. So it's u1 times v1 plus u2 times v2. So it's just a quick little simple formula that has some multiplication and addition in it. Graph the complex number. So remember, the real part is the x and the imaginary part is the y. Those absolute values around the complex number want to know the r value for the complex number. It's the r value that we find when we do trigonometric notation. They want to know how far that point is from the origin. So if we were to plot that point and draw the triangle associated with it, it would be the same as finding the hypotenuse for the triangle. So we'd have a triangle that had an adjacent side of 5, a hypotenuse of 7, and it wants to know, or excuse me, adjacent side of 5, opposite side of 7, and it wants to know the hypotenuse. So the absolute values wants to know the distance that that point is from the origin. Oops. Oh, yeah, I do want to leave it. Ah, here we go. This is the one I was trying to get to. And after this, I think I've pretty much covered everything. I've been ignoring my chat screen. I'm sorry, Riley. Will our vector problems include navigation and bearings? Let me look through them really quick. This one does not. This one's just solve a triangle. Solve a triangle. Find an area. There's an area formula at the end of section 1. This one is graph a polar equation, which you could just easily type into your calculator if you put your calculator in polar mode. Convert the rectangular equation, and I can show you how to do that. Convert. Find the component form. No, it does not look like any of these application problems have bearings in them. None of them. So there's only 2 or 3 vector application problems, and they're all really straightforward. No tricks whatsoever. Not even really like application problems, really just computation problems. I'm going to go back through this direction. That one is like, that one has no bearings in it or directions. That one's not vector. That one really just ends up being a triangle, and it doesn't matter if you do it from north, has nothing to do with north, south, east, west. That one's just components. That one's just solving one piece of a triangle. Solve a triangle. Trig form. Rectangular to polar. Trigonometric form. Nope, absolutely not. So I'm going to go back and I'm going to do that vector problem. This is probably really, really similar to, if anybody saw the video I sent out towards the end of last week. which was probably too late to help you on any of your homework. But it was how to do vectors. Somebody did email me back and say it was completely different than how the Help Me Solve It does it. I really like my way better, though. Let me find my vector problem. So one trick with these vector problems is they only give you one angle. So what you can do is you can assign the other angle to be 0. So I'm going to say that U's angle is 0 and V's angle is 69 because it says the angle between them is 69. Technically, you could assign them to be anything you wanted to as long as the difference was 69, but I would just keep it simple. Let U's angle be 0, V's angle be 69, and then they both have magnitudes. In order to add vectors, you've got to put them into components first. And then once they're in components, we can add them. And then once we have components for the answer, then we'll switch it back to a magnitude and a direction. So we've got 12, 14, and 69. So this was the information the problem gave to us. I'm going to say this is the vector for V. And I'm going to say let U, or that's going to be the angle for V, and let theta's angle be 0. That's the easiest way to say there's 69 degrees in between them. So on a graph, V is pointing up here, and U is down here. And this has got a magnitude of 12, and this has a magnitude of 14. And I want to know what happens if I add them together. And when you add them together, it always ends up somewhere in between. But you can't just say it's going to be exactly halfway in between, and it's going to be the magnitudes added together, because they're kind of pointing in different directions. So 14 is kind of trying to pull up, 12 is trying to pull out. So some of the forces, usually vectors represent forces, some of the forces are pulling away from each other and are counteracting each other. So they're not completely working together. So part of them are working together, part of them are working against each other. That's why we break them down into components. The components are pointing in the same directions. And then we can decide what pieces are working together and what pieces are fighting each other. So I'm going to break U to components, I'm going to break V to components, and then we can combine. So the component formulas, again, are probably going to look familiar. To get X components, you do R, and it's not R. We don't use the letter R here, we do magnitude. To get U sub X, we do magnitude times cosine theta. And to get U sub Y, we're going to do magnitude times sine theta. In our other concepts with polar coordinates and with trig notation, we were putting R in that spot. But it really means the same thing. It's a slanted distance. So you can think of it the same way, and then I'll do the same thing for V. So U sub X, U's magnitude was 12, and it had an angle of 0. So 12 sine 0. And I'm going to do the V's right underneath, because the X components can be combined, because all the X components are horizontal. So they're all pointing in the same direction. V's magnitude is 14, and it's at an angle of 69. And then put V's Y magnitude right under U's. And the Y components can be added together because they're both pointing vertically. And now I'm going to add these together. And I could type that straight in the calculator. 12 cosine of 0 plus 14 cosine 69. And 12 sine of 0 plus 14 sine of 69. This is going to give me components for my answer, which we call the resultant. And I'm going to type that, the whole thing, straight in the calculator. That way I don't mess up any of my answers with rounding. So this one's about 17.017. And this one's about 13.070. So what we have now are the legs of the triangle. We want the hypotenuse and the angle. We want to turn this back into a magnitude in the direction. We've got like an x coordinate and a y coordinate. So now to go back to a magnitude and a direction, or a magnitude and an angle, the magnitude, that's your Pythagorean theorem. So 17.017 squared plus 13.070 squared. I got about 21 points. Let me see how many decimals they want. 10th. I got about 21.5. And then for theta, we're going to do the tan inverse of your y over your x. So that's going to be tan inverse of 13.070 over 17.017. And that one they want rounded to the nearest degree, nearest whole number degree. So I got about 38 degrees. So I had said when I drew the picture that it's going to end up in between. If you cut 69 degrees perfectly in half, that's about 34.5. So it is close to that, but it's not exact. And that's because the vector with the bigger magnitude is pulling harder. So really, this got pulled more in that direction because this vector with the bigger magnitude is pulling harder. So that's why it's not exactly halfway in between. It's actually a little closer to the vector with the bigger magnitude. One way to think about vectors is people pulling on ropes. If you've got two people pulling on ropes that are attached to the same thing, the person that's pulling harder, whatever it's attached to, it's gonna move more in their direction. So it's the same idea. So if these two people, if there's somebody standing here and there's somebody standing here, and they're both pulling on a rope of something that's attached to here, this object it's gonna come somewhere in between them, but it's probably gonna go more in this direction because this person's pulling harder. This person's pulling with a force of 14 pounds. This person's only pulling with a force of 12 pounds. If they were pulling with the exact same force, then it would go exactly halfway in between them. But it always goes in between, and it always is going to tend more towards the one with the bigger force. So it makes perfect sense that it's 38 degrees. And I'm just going to type this in and make sure 21.5 and 38. Good. So I've gone through almost everything now. So you can see the test only has 21 questions. There's a bunch of triangle stuff back from section 1 and section 2 with law of sines and law of cosines. This is literally like a copy of the test. All of your numbers are going to be different. But I mean, these are also the same problems from the homework. So there's a few problems with complex numbers. As long as you know how to switch back and forth between the trigonometric notation and the standard notation, those bars mean we just want the R value, which is the distance from the origin. The dot product is just that formula. Polar coordinates, going back and forth between rectangular coordinates and polar coordinates. Oh, I know what I was going to show you. I was going to do one more thing. I know it's getting late. I'm sorry. How to convert polar and polar equations and rectangular equations. That's one more thing I wanted to show you. And it was back towards the end. So this one, this was not a convert, but this is just see what the graph looks like. There is a way for you to put your calculator in polar mode. If you hit the mode button on your calculator, instead of having your calculator in function mode, if you look across, there is another option that says POL. That is polar mode. And you can put your calculator in polar mode. And if you hit Y equals, it doesn't say Y equals anymore. It says R equals. And you can put negative sine theta in there and see what it looks like. And actually, to get theta in there, you hit the X button. Because if you look at your X button, it actually says XT theta N. And in polar mode, theta will pop up. And then just do zoom 6. It looks kind of like a square. And it's just because it only is plotting so many points. You might want to do zoom trig, actually. Let me see if zoom trig does any better. I probably need to be in radians. That would help. Sorry, I'm playing with my calculator. I just had to mess with my window a little bit. So you can type this, you can put your calculator in polar mode and type that equation into Y equals. I had to reset my window to make sure it was graphing using radians was the trick. Unfortunately, I don't have any way to show you really what I'm doing on my calculator. But I do want to show you these last couple really quick. Converting r cosine theta equals 11 to a rectangular equation. R cosine theta equals 11. So there's some conversion formulas to go back and forth between rectangular and polar. Is there a practice test in Math Labs? There is, but it's not a practice test that I made. It is a practice test that the book made. So it might have a lot of extra stuff in there that you don't need to worry about. It might be a lot more difficult than it needs to be. What I would do is probably just look back through the questions that you're seeing in this video, and all of these questions came from homework, and these are the same questions that are going to be on your test, maybe just with different numbers. Unfortunately, though, they're not all compiled in one place except on your test. So to convert from rectangular to polar, we use r equals square root x squared plus y squared, theta equals tan inverse y over x. We've been using those over and over and over again. To convert from polar to rectangular, we use x equals r cosine theta, y equals r sine theta. So in this problem up here, they want us to convert it to rectangular. So to convert from polar to rectangular, we use these formulas. So if we see any of that stuff in there, we want to replace it. And I see r cosine theta. I see r cosine theta. R cosine theta is equal to x. So I can replace r cosine theta with x. So this is just x equals 11, which is a vertical line. So anytime I see this stuff, I can replace it with that. There's another one here that works a little bit different. So there's our option there, x equals 11. The next one's a little bit different. It says convert x squared plus y squared equals 16 to a polar equation. So x squared plus y squared is right there, but right now it's under a square root. So I could replace that entire chunk if I could just get rid of that square root. So think about what you would do in algebra to get rid of a square root. We would square both sides. So I'm going to adjust that a little bit so that I could use it in this problem. If r is the square root of x squared plus y squared, that means r squared is equal to x squared plus y squared. So this entire chunk right here can get replaced with r squared. And usually with polar equations, we want to solve for r. So you can square root both sides. And the nice thing about polar equations is when you square root, you do not have to put a plus or minus in front. This is just r equals 4. R is a distance, and we don't have to consider negative distances. If we want to go in the opposite direction in polar coordinates, our theta will take us around to the other side of the graph. So we don't have to use like positive equals go right, negative equals goes left. R is a distance. R tells us how far to go out from the origin. So we don't have to use plus or minus. So this is just r equals 4. X squared plus y squared is r squared if we go ahead and get rid of that square root. And then replace x squared plus y squared with r squared, and then polar equations, we like them solved for r if possible. So we square root both sides and get r equals 4. And that is one of our options. And then this last problem wants us to take 2 points and turn it into a vector in component form. It says create vector mn. So again, the way that they name those vectors is the starting point to the ending point. So vector mn, it goes from 7, -8 to -6, -2. So component form for a vector is the 2 sides of the triangle. It's how horizontally we get from m to n and how vertically we get from m to n. So I'm going to show you this on a graph. So 7, negative 8 is down in quadrant 4, and then negative 6, negative 2 is in quadrant 3. So I need to make sure I've got plenty of space down here. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So here is 7, negative 8. And then 1, 2, 3, 4, 5, 6, negative 2. Negative 6, negative 2. We're going from M to N. And a vector is just a hypotenuse of a right triangle. The components are the legs of that right triangle. So how do I get there if I do it in 2 steps instead of 1? So go horizontally and then go vertically. Split it up into 2 pieces. Horizontally and then vertically. So first, what do we do in the x direction to get from 7 to negative 6? To go from 7 to negative 6, I need to go left 13 units. So that is negative 13. And then to get from this y coordinate to this y coordinate, that's from negative 8 to negative 2. I need to go up 6 units. So that's positive 6. So vectors have direction. It matters where you're starting and where you're ending. If I was going the opposite direction, I'd be going down and right, and the signs would change. So it's really important that we understand that we're going from M to N, which means I have to go left and up. That's why the x is negative and the y is positive. We had to go left 13 and up 6. So the components, those are just the legs of that right triangle. The actual vector is the hypotenuse. The components are negative 13 and 6. And then it wants to know the length of the vector, and the length of the vector is just Pythagorean theorem. So I know I've got one side of negative 13 and another side of 6, so the length for this side is going to be the square root of negative 13 squared plus 6 squared, which is 169 plus 36, which is radical 205. Radical 205. One way that you can check in your calculator to see if that square root simplifies is you can go to your y equals, and in y1, you can take that number and divide it by x squared. Because to simplify a square root, what we're trying to do is see if there's any perfect squares that will come out of it. So in y1, type your number divided by x squared and go to the table and start at x equals 1 or 2. Really, 1 doesn't matter because it's going to say 1 and 205. And go until you get to like a y value of 1 point dot 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 dot, because those don't matter either. See if there are any whole number pairs, and you want to find the biggest possible. If you see any whole number pairs in this list, then that radical will simplify. The x is what comes out and the y is what stays in. So I'm going to check this one in my calculator. So 205 divided by x squared And in my table, when I scroll down my list, don't worry about the negatives because we don't ever pull negatives out unless we're dealing with complex numbers. There are no whole number pairs in my table. That means radical 205 does not simplify. So that's as good as it gets, radical 205. If you want to see an example that does simplify, let me see real quick. Do square root of 384. That one does simplify. And I'm going to go back real quick and put in square root 205. So to simplify square root 384, you can go to your y equals and type in y1 equals 384 divided by x squared, and go to your table and look down your list and see if there's any whole number pairs. And there are several. There's 1 in 384. There's 2 in 96. You want to use the biggest x possible because the x is what comes out. There's 4 in 24. There's 8 and 6. And then once your y value gets below 2, you're done. You don't have to look anymore. That's the biggest one. So radical 384 simplifies to 8 root 6. It's always the x comes out, the y stays in. So that's a really fast way to simplify radicals on your calculator. So I'm going to post the video for the people who were not able to come, and I'm also going to post these notes in case anybody wants to print them out and use them. I also suggest printing out some of your homework, or at least having the notes from your homework when you do your test. The test is not long at all. It's only 21 questions. But some of the questions have multiple parts, like solving the triangles. There's several things to find. So that's part of the reason it's quite a bit shorter. But you've pretty much now seen the test. You've pretty much seen the test. All it's going to do is change numbers. So hopefully nothing will be a surprise. So I hope this helped at least a little bit. And just let me know if there's anything else I can do for you. And I hope y'all have a good night. You're very welcome. Do you have any questions before I go? I'm not really in any hurry. All right, have a good night, May. Riley, are you still there? It's just usually the one thing that most people struggle with is they round too early. So when I go back in and I check the tests for partial credit, most of the time people are on the right track, but MyLabs Plus marks it wrong because their answers are off by a little bit. So if the answer was supposed to be like 1.375, they rounded too early, and then they kept using a rounded number, and then they ended up getting like 1.3 369. So usually people get really close with their answers, and I think it's just a rounding issue. So if there's any way that you can keep your answers exact all the way till the end, or if you can keep the full exact answer, decimal answer in your calculator, and keep using it by hitting second and then the negative button on your calculator, that will tell your calculator to keep using the previous answer. That way it doesn't round it along the way. That will help. But I always go back in and I give back most of the credit for those. But I know some people get really discouraged because MyLabs Plus will automatically count the whole thing wrong, and then they see a terrible grade, and then they have to wait for me to go in and do partial credit for it to go back up. And but that's one thing that usually gets people is the rounding. Be really careful with the extra blue instructions underneath the answer box. Some of the questions in this chapter want the answers in radians, and some of them want them in degrees, so just be careful with that. I know with the complex numbers, I saw that several times where some said put them in radians, some said put them in degrees. With the polar coordinates, some said radians, some said degrees. But that's about it. People usually do really bad on those vector questions, so that's why I made that extra video that I sent out. I sent it out really late last week. I'm sorry. But usually people get really confused with adding the vectors together. So I sent out the vector video about adding the vectors together by breaking them into components. So if you can break them into components and then add them together and then put them back into magnitude and direction. I hope you do too, Riley. Have a good night.